We'll be learning a problem, how to train up using this backpropagation algorithm, and what are the other types of multi-layer feed-forward neural networks. So, using backpropagation algorithm to train two-layer for XOR problem. Okay, this is the problem given to you. Please note down, all of you. Please note down. Your input vectors given 0, 0, 0, 1, 1, 0, 1, 1. And desired response is 0, 1, 1, 0. Nothing but truth table of XOR gate. Okay, here you are considering the two-layer network has one output. Okay, the activation function we are considering of hidden units we are considering here is sigmoidal activation function. Okay, which is given as HA is equal to 1 by 1 plus exponential of minus 5A. So it's a derivative form. Okay. Hope all of you are following. Please note down. You are using backpropagation algorithm to train up two-layer for solving XOR problem. Okay. So the neural network has a two-layer network with one output, single output. Function is given. Your activation function you are using is a sigmoidal activation function. So derivative of this sigmoidal activation function is in simple form h dash of a is equal to 5ha into 1 minus h of a. So you have output loop, inner loop, back propagation. You need to propagate your error signal to all the neurons present in your input layer. So updating your weight vector. So these are the steps you need to follow in the back propagation algorithm. So you are updating your weight vector. So you are ending your inner loop until last data desired sample output is updated. So first training pattern forward propagation using forward propagation. First your training pattern using forward propagation. So first A J of 1. You have two inputs. Okay, two inputs. So summation of I from 0 to 2 Wji xi. And considering the activation function, your sigmoidal function 1 by 1 plus exponential of minus 5 aj. So for second input, you have two input neurons. Okay, in the input layer, you are considering two neurons. So you need to calculate aj of 1, aj of 2. Okay. So computing delta for each output unit using delta is equal to y minus t. Now we are propagating to this delta for the hidden units using your derivative of your sigmoidal function. Okay, derivative of sigmoidal function. That is delta j is equal to 5zj into 1 minus zj into wj delta. So next, derivative with respect to first layer and second layer weights mentioned as dou En by dou Wji delta j xi, dou En by dou Wj delta zi. Here, instead of considering directly error, we are considering mean square error. Okay. So for this mean square error, we are plotting for different values of eta. Your training, see, you can observe from this graph, your training patterns are considered for 1000, 2000, 3000, 4000, 5000 epochs, training epochs. So you can observe that when eta is increasing, the mean square error is reducing. Here, you can observe that when eta value is 0.05, the error is least occurring within minimum number of epochs, that is iterations, minimum number of iterations. Whereas for 0.02, you need to train up your neural networks almost 3000 times instead of training up to only 1000 times when eta is increasing. Okay. So the weights, finally, the weights converged with simple code, you can generate this. Okay. So you need to see our XOR output is desired output is 0, 1, 1, 0. But network output you have obtained is 0.99, 0.009, 0.009, 0.98. It is just the reverse. So you need to transfer the error back to each neuron in your hidden layer as well as input layer and train up your network again with the modified weights and then forward propagate to obtain your desired output. Okay. Your net desired output is 0, 1, 1, 0. But here you can observe it is 0.99, 0.009, 0.009, 0.98. Just reverse. Okay, so you need to train up multiple number of times the same network in order to achieve the desired response. The error should be back propagated. I have shown you in the last class. Let me show you again. In the back propagation algorithm, we have learned that in this backpropagation algorithm. Once you are evaluating E value W1 x1 plus W2 x2, you are feeding this to your nonlinear element, which is giving you your output y is equal to f of e. So you need to train up your neural network. Okay, your training data consists of two input signals assigned with corresponding target value. Okay, the network training is an iterative process. You need to repeat your iteration until you get your desired response. Okay, in each iteration, the weight coefficients are modified using the new data from the training data set. Okay, so you know this, you have clearly understood that the in the back propagation algorithm, first you are going to calculate the outputs in the forward part. Okay, y1, y2, y3, y4, y5. Finally, y6. So after calculating your y6, you need to verify whether your output signal of the network is achieving is the achieved desired value or not, whether it is matching your desired value or not. That is, you are calculating delta. The difference is called error signal. Okay, your desired value as well as your calculated output value. The difference you are comparing. If it is achieved, you need not go for back propagation. Okay, but definitely it will not achieve the desired value. So you need to propagate this error. Okay, this error through all the neurons in each layer. In the hidden layer, here for your easy understanding, we have considered only 3 input neurons and 2 hidden neurons and 1 output neuron. So the error should be propagated, must be transmitted to each neuron in the backward direction in order to update your weight coefficients. Okay, so here you have already learned this in your last class. You are transmitting the error to all the neurons in the hidden layer as well as to the input layer. So once the error is transmitted, you need to calculate the weight coefficients with the modified values. So for the modified values, the weight's modified value can be evaluated using this Wx11 is your old weight value, eta into delta 1. The error calculated at the first input neuron and derivative of your function. First derivative of your function into xy. Likewise, your other weights are also modified. So once all the weights in the input layer, in the hidden layer are calculated, up to output layer, the weights are recalculated. Next, you need to verify, you need to calculate again the F1, F2, F3, F4, F5 and F6, and you the output y you need to cross check whether the desired output is achieved or not with the new weights values. Okay. here the weight vectors converge. First hidden node, second hidden node, output node. Randomly, they have mentioned the weights values here for two different eta values. They have considered directly not the error. They have considered mean square error. Mean square error. Okay, for your understanding purpose only, I am giving you this example. So next, what are the limitations? What is the need to go for other types of multi-layer feed-forward neural networks? In the so there are some limitations for this backpropagation algorithm. So one more example is mentioned here. I'll share it to you. This one you can go through the example and understand clearly. So this backpropagation algorithm is based on minimizing the error of the network using the derivative of error function, which will be very simple, slow, and also there may be issues relating to local minima. Okay, while going for number of iterations, there is possibility of missing the local minimum value. So preferably we go for most common measure of error is mean square error value. And we also evaluate partial derivatives of error with respect to weights at the output neurons, hidden neuron, as well as input neurons also. So calculation of this derivative flows backward through the network. So the name have come as backpropagation algorithm. So this derivative points in the direction of maximum increase of the error function. So a small step change in the learning rate in the opposite direction will result in maximum decrease of error. Okay, here eta value, earlier we have seen eta value or it may be alpha value also. So a small change in this learning rate, a small change in this learning rate may decrease your error function. So the learning rate is very important in your backpropagation algorithm. It is too small for convergence, extremely slow value. Too large. The learning rate is too small means the convergence will be extremely slow. If it is too large, may not converge. Okay, you are asked to write what are the difficulties encountered in the learning rate of backpropagation algorithm. So you need to write these steps. The derivative points, you need to calculate derivatives backwards through the network, hence the name backpropagation. These derivative points in the direction of maximum increase of error function. A small step change will result in maximum decrease of error function. maximum decrease of error function. So the learning rate is very important in the convergence of your error. Okay, if the learning rate is very small, the convergence extremely slow. If it is too large, it may not converge. Okay, so you need to go for certain modifications in your learning rate to get your convergence quickly and accurately. Quickly and accurately. Applying smoothed averaging to the change in weights, which is your momentum coefficient. We are going for another assistance for convergence is momentum. Okay, we are going for small or smooth averaging change in the weights. That is delta nu. Beta delta old minus alpha into dou E by dou WO. You are modifying your old weight value with a momentum coefficient so that your convergence can be accurately obtained. Okay, this is mostly used in your low pass filters for reducing rapid fluctuations. So local minima. Another point, another drawback for backpropagation algorithm is training is essentially minimizing your mean square error function. Okay, you need to avoid the problem in finding your local minimum. So some of the techniques for avoiding this local minima are simulated annealing, optimization techniques. Okay, the weights in progressively smaller amounts. You are changing your weights with smaller variations. Another method for avoiding local minima is genetic algorithms. Use the weights as chromosomes, apply natural selection, mating mutation to these chromosomes. So you have these are some of the drawbacks in backpropagation algorithm. So preferably we are going for another type of networks, counter propagation networks. Okay. This is another multi-layer feed-forward network. It is 100 times faster than your backpropagation algorithm. Not as general as your backpropagation. It is made up of three layers: input layer, component, and Grossberg layers. Okay, this is the architecture of your counter propagation network. So, how this Kohnen layer, how this Grossberg layer will be operating, we'll be learning one by one. So, in the Kohnen layer, neurons in this layer sum all the weight inputs received. The neuron with the largest sum outputs 1, and the neurons with output other neurons with small sum will be 0. So all the weights are summed up in your Kohnen layer. Whereas in Rosberg layer. Each neuron outputs the weights of connection between itself and one active common neuron. So it is taking one active common neuron and itself, weights of itself. So why we are going for this different types of layers is you have more accurate representation corresponding to your biological neural network. So the coronal layer and Rosberg layer has its own distinct purpose. The coronal layer separates inputs into separate classes. Inputs in the same class will turn on the same coronal neuron. This Grossberg layer adjusts weights to obtain acceptable outputs of each class. So, how to train up a counter propagation network? You need to train up your coronal layer as well as Grossberg layers also, neurons also. So, training up coronal layer, you are using unsupervised training. The input vectors are often normalized. One active common neuron updates its weight according to the formula mentioned. W nu is equal to W old plus learning rate alpha or eta. You can go for any of this input minus W old. The weights are modified more closely to match the values of input. At the end of the training, we need to consider average values of inputs in that particular class. So coming to training your Rosberg layer, you are using supervised training. In this, the weight update algorithm is similar to the backpropagation algorithm we have learned. So hidden layers. Okay. So for most of the problems, we consider only one hidden layer. But when we go for complex problems, there may be multiple number of hidden layers. Okay. Suppose if your function is discontinuous, you consider two hidden layers. Right? The number of neurons in each hidden layer are also important. So if the neurons are very less, number of neurons are very less. So the neural network cannot learn the complete details of your data, input data. If there are more number of neurons, so the neural network may contain insignificant details. So sufficient number of neurons are to be selected. That is very important. So overfitting can occur if a good training set is not chosen. What is meant by good training set means samples must represent general population, must contain members of each class. The samples must contain members of each class. Yes, that is, they should contain wide range of variations or noise effect. Then only you can have your good training set. So the size of your training set is related to the number of hidden neurons. Okay, 10 inputs, 5 hidden neurons, 2 outputs. So definitely you have 67 weights. 11 into 5, 55 plus 6 into 2. So if only 10 training samples are used to determine these weights, the network will end up being overfit. Okay. Any solution which is found will be specific to 10 training samples. So if you have 67 unknowns, the weights, we should come up with some solution. You cannot find the general solution for the given information. So definitely all known samples are split up into training set and testing set. Okay, a group of samples used to train your neural network is called training set. And a group of samples used to test the performance of your neural network, which is used for estimating your error rate, are called testing set. So once you are training and testing, you need to go for verification of your neural network output, whether the desired output is obtained or not. Verification. So after verification, if the errors are the desired output is not achieved, you need to propagate your error to your all the neurons in your hidden layer as well as input layer also. So there are some other techniques for estimating the error rate of neural network. Okay. Those are cross validation and bootstrapping techniques. So finally, you will be getting your result. So we have discussed how the learning rate is affecting. What are the difficulties encountered in the backpropagation algorithm due to the learning rate, and also counter propagation network, in which we have Cohen layer and Grossberg layer. Okay. In the multi-layer feed-forward networks. So in next class, in continuation with this, we will be learning radial basis function. Okay, in your third unit, you have radial basis function, neural network, and Cohen self-organizing feature map, KSON. Next, associative memories. In continuation with that, we have associative memories. So you can ask any queries. If you have any queries, you can type in the chat box.